So welcome back. So we talked about modulus. So far we talked about compression test. Under compression, the modulus is Young's modulus or compression modulus, whatever way you want to call it. So I also said in the shear, you get the shear modulus, right? When you are shearing samples, even in the compression test, most of the failure occurs because of the shearing. So those modulus is called shear modulus. Modulus relating shear stress over strain is called shear modulus. And if you are sinking some body in the water, the pressure caused by the weight of the water compresses it, and that's called the bulk modulus. So uniform deformation caused by a change in external pressure is called volumetric strain. So from that you can calculate the modulus relating hydrostatic pressure or volumetric stress over volumetric strain. This is called bulk modulus. Typically, we do not use this shear modulus, bulk modulus for any practical situation. We use only compression modulus or Young's modulus. That's the bottom line, because these are all very difficult to do the testing and collecting data and then relating them. They may not have any practical significance, but it's worth knowing about that so that you all know the what's the different moduluses happening in actual biological materials or food materials. So let's revisit the Hooke's law again. Stress over strain ratio or slope of that line gives you the Young's modulus or modulus of elasticity. So it is from force over deformation. This is spring constant, and then modulus of elasticity is stress over strain. So it's always stress is proportional to this. For within the elastic limit, stress is proportional to strain, and proportional to constant Young's modulus or modulus of elasticity. It's a material property. Because it is stress over strain, the modulus elasticity or material property has the same unit, right? Because stress is Pascal and strain is meter over meter, cancels, you get Pascal or kilopascal or megapascal, like that. Typically, modulus, Young's modulus values are in megapascal units only, not kilopascal or Pascal. What is PSI? Pounds per square inch. Okay, I'm glad you know, because when I teach my students, they can relate PSI very well, because in US we use pound, inches, feet, like that. Here it is kg, meter, like that, SI units. So that's why I put both the units there. Okay, some of the modulus of elasticity values for different materials is a ratio of the stress over strain again within the elastic limit. So corn sample, low moisture has a higher elastic limit, more stiffness. Higher moisture has a lower modulus of elasticity, because higher moisture will be less elastic, so less stress and for the same strain level. Wheat has similar number when you look at the moisture content, but still it's higher number for its lower moisture content. Soybean is much lower modulus of elasticity. Why this much different? Primarily because how these material are produced. They have ingredients, they have their own differences because of the composition of the product. They have different carbohydrate, protein, fat, things like that. So that makes this much different. Potato has a lower modulus of elasticity values. Melon has a much lower value, and then bone has a much higher value. So bones are much stiffer. Higher modulus of elasticity value means much stiffer. That's what it is. Are more harder also. I mean, you can look at them different ways also. Not only stiffness, hardness also play a role also there. Okay, now we are going to do some calculations. So far we talked about data, but you didn't see any data yet. So now you got the data. we are going to calculate the modulus of velocity when a 50 mm cylindrical sample, long cylindrical sample by 20 millimeter. So, this is 20 millimeter and this is 50 millimeter. It compresses 0.5 mm when you apply the 20 Newton force. So, deformation is 0.5 mm. It is not to the scale, right? 50 mm here and then my 0.5 mm is here. So, it is not to the scale. So, we want to calculate the modulus of velocity. It is a function of stress over strain. So, what is how do you calculate the stress now? Force over area. Okay. Let us do the force over area. Force is 20 Newton, you apply, divided by area is pi r square, right? Because this is the area. Sorry. This is the area which is pi r square or pi d square by 4. Either way, same thing. So, pi times 10 millimeter square. All of a sudden it is jumped, right? 10 millimeter square is basically 100 millimeter square, and then to meter square it is 10 power 6. So, it is, if you use your calculator, 20 divided by 3.14 times point 100 millimeter square one meter square is 10 power 6 millimeter square, right? So, millimeter square cancels. This 20 divided by 3 gives you 6.4 times 10 power 4 newtons per meter square, or 640 kilopascal, or 64 kilopascal, or 0.064 megapascal. Got it? You all got the same number? If you would have been in my class, we will be sitting here for next 10 minutes, because sometimes people do not know whether to multiply by 1000 or divide by 1000, because they are not used to these calculations, these numbers crunching things. So, for them it is difficult. So, we got the stress value. Now, we need to calculate the strain value, right? So, strain is deformation is 0.5 mm divided by 50 mm, mm and mm cancels, 0.0501 is strain. So, elastic modulus, I am going to put this 0.01. So, 0.064 megapascal over 0.01, you get the 6.4 megapascal. Straightforward, right? As simple as cake or as simple as tea. These similar calculations apply to any sample size and anything you can think of. There is no differences. You just need to follow the right units, cancel the units so that you can get the right modulus of elasticity. So what will happen if you keep compressing the sample? Instead of 0.5 mm, if you go to 1 millimeter or 2 millimeter or 3 millimeter deformation, what will happen to the force? Force will be increasing linearly, right? We are still in the elastic limit. You should be increasing. So your modulus of elasticity value should be the same. Yes, because if your curve is like this, stress over strain. So whatever you do within this elastic limit, your slope should be the same slope. Whether you are getting it here, getting it here, getting it here, like that. Make sense? Okay. Everybody same page, right? Okay. Let's look at the Poisson ratio now. When a specimen is compressed in one direction, what happens other two directions? Here only another direction, it will increase. So lateral strain over axial strain, normal strain is Poisson's ratio. So when you look at the Poisson ratio, it can vary from 0 to 0.5. The maximum Poisson ratio is 0.5. And those samples are called incompressible material. 0 means full of air spaces. So popped corn may have very close to 0. Cheese will be close to 0.5 because there is no pore spaces in cheese samples. So if you compress them, they will not compress. So that's why the Poisson ratio is 0.5 for the cheese. Incompressible. Potato has less porous, so it's 0.45 to 0.49, but cheese is 0.5 most of the time. Easily compressible, cork very porous, Poisson ratio is 0. Popped corn also will have Poisson ratio of 0 because it's incompressible. You cannot compress them. That's why its Poisson ratio is 0. Apple 0.21 to 0.29, more porous, that's why. Anybody has any other material we want to guess their Poisson ratio?
If we have any expanded snacks, what about that?
Expanded snacks, depending upon how much pore spaces you have. Cheetos will have a Poisson ratio of 0.1 or 0.05 because it has more spaces. Cheetos, right? Make sense? And then if it's a very dense product, Poisson ratio will be 0.2, 0.3 like that. Dense extruded snacks, things like that.
That's a proportional relationship.
Yes, like for example, if you are deforming the sample, it's going to deform one way and then it's going to expand in another direction. So it's the ratio of those two strains will give you the Poisson ratio. Any other questions anybody has?
Will this Poisson's ratio has something to do with product development?
Definitely, yeah, very good question. The question is, will the Poisson ratio will have impact on food product development? Definitely it will have. And again, these things will dictate depending upon the consumer perception, consumer preference also. So you can develop a dense product which will have a Poisson ratio of higher Poisson ratio, which is less than 0.5. The maximum can be 0.5. Less than 0.5, you can make the product, which is denser product. On the other hand, if you want a buffed product, then your Poisson ratio will be less than 2 or 0.2 or something like that. So this can be used for when you are trying to develop the products, then you can measure the Poisson ratio if you have opportunity to do that, right? Because you have to measure the what happens to the lateral direction to the product. So you should be able to measure it while you are doing the force deformation compression testing. So you need to have some type of strain gauges or LVDT. You can measure that how much strain is happening. So from that strain value, you can calculate the Poisson ratio.
It's like in the previous two slides we saw that corn at 13.3% has a 400 Pascal, and whereas at 18.7% it has 219 millipascal. So how is the Poisson ratio going to be interrelated with or play a role?
Okay, the question here is, in this slide, I showed you modulus of velocity values for the corn with the low moisture content, 400 megapascal. With the higher moisture content, the modulus of velocity is 219 megapascal. The question here is, if you calculate the Poisson ratio for these two samples, how they will relate? What would be the Poisson ratio for this sample and for this sample, right? That's a question here. So when you theoretically look at these things, 13.3% moisture content will have more pore spaces. Low moisture, so it will have more spaces within the corn itself. This 18.7% moisture content will have a less pore spaces compared to 13.3% moisture content. So less pore spaces means it is more lower Poisson ratio. No, other way around. Less pore spaces means higher Poisson ratio. More pore spaces means low Poisson ratio. So this is low Poisson ratio. Less pore space, higher Poisson ratio. Make sense? I mean, these are all hypothetical cases we are looking at, right? Until otherwise we go and test the sample. I mean, this should hold true because when you have more moisture, less pore spaces, so this is supposed to be working correctly. But again, these are all for individual corn samples. Then you need to have a proper experimental setup to measure the actual Poisson ratio. Because a Poisson ratio is a ratio of the two strains, lateral strain and normal strain. So that needs to be calculated or measured. I mean, if you can measure other things, you can calculate the other things. You cannot calculate everything without the measurement available. That's a limitation also, right? You cannot really calculate everything without any available information or any information needed. If that information is not available, then you need to collect it so that you can determine the other properties. One more question.
So if we look at here, so while we are going for the milling, it is the hardness which resists it. So we prefer low moisture content. So here it's like at 13%, there will be a kind of milling and higher starch damage. But why we go for the higher moisture? Why?
Oh, okay. The question here is why we have a corn with a higher moisture compared to low moisture. That's a very good point, because when you are trying to when you do the milling process, you don't want to do a higher moisture content milling because it takes more energy to grind them. The powder, making powder, then you need to dry the water out, things like that. So low moisture will produce better better flour for after milling and all. The measurements they did was when you harvest the corn or soybean or wheat, those are all harvested after the during the fall time, where there could be some precipitation, could be rain or snow, things like that. Typically, when they harvest the corn from the field, they will have a higher moisture. That's why they cannot. And also, the time of harvest is depends upon the market value for their product. If the market value is low, they will not harvest the corn. They will leave it in the field until market is ready to, they can make more money out of economical conditions that time. So they try to leave the corn in the field as long as they can keep it in the field. So that's why they end up harvesting at a higher moisture. Then they store it during winter time, and then when the economy is good, then they sell it for the market. So because there people have 600 acres, 1000 acres, 2000 acres, that's a land size they have. So they produce a lot of corn, soybean and wheat like that. Not like here. There everything is massive. Tractors are big, harvesting equipments are very big, and that's a reason they harvest the material at a higher moisture content. Make sense? Things are different in different places, but it takes time to understand everything. There is a reason for having, there's no reason for them to put water into the corn, right? Why you want to do that, right? If it is a natural thing, then you need to worry about reducing the moisture, which they will do it if they need it. Sometimes they, instead of spending money in drying the material and selling it, they just like that sell it to the market. A lot of times from corn, I don't want to change the subject here, but I just want to make sure that I want to talk about this also this time. So when you in US, in Midwest, we produce a lot of corn, and most of the corn they use it to produce ethanol, because it has a lot of starch. It's a very proven technology to economically produce ethanol from corn. So there's a lot of industry there, ethanol industry. They take corn and they produce ethanol. So depending upon the market value, they try to, so they can still sell the high moisture corn to the ethanol industry. So they don't get tagged, they don't get reduced in terms of price because they have more moisture. Because the ethanol industry would like to have the high moisture corn so that they don't have to add water in the process. So it's a win-win situation for both the ethanol industry and also farmers. So that's a difference there. Any other questions? Feel free to keep asking me. Okay, we are done with this exercise, right? We just calculated it. Okay, Poisson ratio, we talked about it. Okay, some of the Poisson ratio values for different material: gelatin 0.5, incompressible; rubber, potato, corn endosperm, glass, apple, cork. Okay, one more problem here. Let's do this problem. Somebody wanted to do the cubical samples? Let's do cubical sample now. Okay, now we have example is apple cube has a side length of 20 millimeter. Side length is 20 millimeter cube and is subject to a uniaxial compression force of 98 Newton, uniformly distributed over two opposite faces of the cube. I am not sure how it happens, but it's an example, right? It's a hypothetical case. So what it says is, when you compress a sample, the 98 Newton get distributed uniformly into two opposite faces of the cube. So you have to measure only one strain. You cannot calculate only one strain, so that you can calculate the predict the dimensions of the deformed cube. You assume apple has an apparent modulus of velocity of 5.15 megapascal and a Poisson ratio of 0.23. Again, this is all hypothetical case. So we want to predict the dimension of the deformed cube. How we are going to do that now? Modulus of velocity is given, Poisson ratio is given. So from modulus of velocity, we have the force acting on this side. So you take a force over area, you get the stress value. We know modulus of velocity. From there you can calculate the strain in one direction. So you have strain in one direction. You have Poisson ratio. You can find the strain in the other direction. And from that you can find the dimensions of the deformed cube. Make sense? Let's do one by one. Stress is force over area. Force is 98 Newton and the area is 20 millimeter by 20 millimeter. 98 Newton is force, 20 millimeter by 20 millimeter. That gives you 0.245 megapascal. So 98 divided by millimeter 10 centimeter, 0.02 times 0.02. Newton per meter square, Pascal. So this answer will be 245,000 Pascal divided by 100,000 gives you the megapascal. I mispronounced, it's not 100,000, it's 1 million, right? From Pascal to megapascal, 10 power 6. So you should get 0.245 megapascal. Everybody got the same number? Easy enough, right? Okay, now we got the strain, so we can find the deformation on one side. So elasticity is nothing but stress over strain. So strain is equal to stress over modulus of velocity. So 0.245 is the stress. We calculated. So this is 0.245 is the stress divided by modulus of velocity 5.15 megapascal. So you get less than 0.245, which is 0.048 strain. So we take 0.048 and then multiply by height, 20 millimeter, you get 0.96 is the reduction in height. So 20 minus 0.96 gives you the final height of 19.04 millimeter. So this is for one side. the other two sides have the same deformation. The expansion in other two directions are same. That was the assumption given in the problem statement. So what do you think the width, the other two width will be happening? Will be more than 20 millimeter or less than 20 millimeter? More than, okay, got it. You guys woke me up. When you get excited, that's what happens. So, but I mean, it's a good thing to do, you know. I'm glad that you guys are talking, so it's always good thing. Lot of times back home, it's very difficult to make people to speak out. I got to really point people, you speak like that. So I see more energy here. So let's do the calculation for other side. I'm going to go to the next screen. Same information. So Poisson ratio is nothing but the lateral strain over axial strain. We have Poisson ratio calculation 0.23, and from there axial strain we already calculated previously 0.048. So lateral strain will be 0.011. So from this you can calculate the change in width. So multiply by the width, which is 20 millimeter, 0.22 millimeter. So final width would be 20 plus change in width, which is 0.22, 20 plus 0.22 millimeter, 20.22 millimeter. So if you compare this data, 0.2 millimeter increase in the other directions, two directions, but 0.96 millimeter decreased in applied force applied direction, right? 0.96. Here it is 0.22 increase. That's why in the first place I said it's complex situation. We are approximating things here, right? 0.96 and then we get 0.22 in both directions only. So where did the other things go? I don't know. Right? It doesn't equate, but we did the calculations correctly and that's what it is. I mean, volume is same, right? I mean, we are assuming that it's incompressible material, right? Incompressible material. No, it's not. It's a compressible material because Poisson ratio is 0.23 only. So that is why we probably lost some of the deformation, right? It's 0.23 Poisson ratio. So a lot of pore spaces, air spaces there. So when you compress it, more goes down and then less comes out. More goes down, less comes out. Questions? Keep talking. Tell me. Ask me. No? Okay. Speak up. Yeah? Okay, explain it. Okay. The question is, what is del W means here? Del W, delta W means, delta means change in width. That's what the delta W is. Same like change in height. In previous case, delta H means change in height. So when you compress a sample, the height from originally 20 millimeter, there is going to be a decrease in height. Instead of 20 millimeter, it's going to be 19.04 millimeter. So that's what delta, that's a question. Your question is what is delta H means, right? Only delta W. Okay. The question here is, she can understand delta H, that's good thing. So when you have a decrease in height, delta H change, what happens is the width in other two directions that increases. When it decreases, these two width will be increased because same volume, right? Not same volume, but there are more spaces, so that can be accounted for when you do the actual compression. So increase in width will be 0.22 according to the calculations, but in both directions. Other questions? Okay, now we are going to talk about non-Hookean behavior. Basically, our biological materials, food materials, those fall under non-Hookean behavior. Whatever we have done so far, we assumed they are elastic material up to this point. And that's why it's called apparent elasticity. They are not actual elasticity. Apparent elasticity. So this is elastic region. I mean, even that's also assumption only. You have to really do the test and find out under what strain level they will follow the same path. Right? But we are assuming that this is elastic and this is plastic. So total strain has two parts, elastic part and plastic part. The elastic strain is recoverable with no perceived damage. With the classic example, is plastic strain is not recoverable due to permanent damage of the sample. So if this is your stress over strain data, so this is your loading curve. So this is loading and then this is unloading. If you really look at this thing, if you really think about this data, only this probably the only place you can come back the same curve. If you allow me to do that, only this much can be recovered. But when you go this far, then there's always loss of energy. You cannot get it back because of the plastic nature of the material. Here we are talking about only the solid material. Only the solid material. I mean, when I say solid material, only the elastic component. No, not sorry, it's not even elastic component. Elastic components only up to this point, but this is also plastic here. So whatever energy you cannot recover, that's lost energy. Here we are not talking about rupture at all. We are still within the yield point or something like that, but still because of it has a viscous nature and that is not recovered. So in terms of the elasticity of the material, that's why we are talking about elastic and plastic. We don't have to go to dynamic rheology to differentiate the elastic component and viscous component. That's a different classical approach. Here we are just talking about in terms of the elasticity and plasticity. Because we are talking about the solid material, so we didn't talk about the liquid component at all. It's purely elastic discussion here. That's why we are talking about the elasticity and plasticity. So don't get confused. This is totally different way of thinking, so that you can really understand, not even worrying about. If you don't have the rheometer and things like that, you can still do these kind of tests and differentiate between the elasticity and plasticity. Make sense? so that you can account for the other non-elastic component of your material. So because it's not elastic material, pure elastic material, that's why it's called apparent modulus of elasticity. So apparent modulus of elasticity is maximum stress over maximum strain. So this is maximum strain and corresponding strain is maximum strain. So modulus of elasticity and apparent modulus of elasticity, so you can always do this loading and unloading test, and you can calculate the modulus of elasticity based upon whether you use the secant method or tangent method. So let's say you take a point in the loading curve and draw a tangent line and take a slope of this line, that is called tangent modulus of elasticity. And then if you consider this initial point and point of this interest point and draw a line and take a slope of this curve, that is called secant modulus of elasticity. This is two different ways of thinking. Calculating modulus of elasticity, assuming one is secant method, other one is tangent method. Which one is right? Both are right. As long as you do the same thing for all your sample testing, then you are good to go. Again, these modulus of elasticity values, those are all apparent. They are not actual modulus of elasticity. Until otherwise you can identify a point and then both loading and unloading the same curve, then it's still apparent modulus of elasticity, because we are assuming this material are elastic material, which are not. Did I confuse you enough so that you cannot sleep tonight? I hope not. I mean, I hope you are getting the point here. So I think you need to appreciate the differences in elasticity, modulus of elasticity and apparent modulus of elasticity. Only if you consider the elastic, purely elastic material and calculate the modulus of elasticity and their actual modulus of elasticity. On the other hand, our food material, they are not purely elastic. They cannot be purely elastic, and we don't want them to be purely elastic because we cannot eat them, right? So they are called apparent modulus of elasticity. Questions? So from this data, you can calculate the elastic strain, plastic strain. Whatever you don't recover, that's called plastic strain. Whatever you can recover, elastic strain. And from these values, elastic strain over total strain, you can say percentage of elasticity, percentage of plasticity. Or you can get the area under the curve. This area over total area gives you the percentage of plasticity. No. This area over the total area is percentage of elasticity, and this is the last energy, which is plasticity. Because this cannot be recovered. This is all lost. So this area under this curve is percentage plasticity, and the area under this curve is percent elasticity. So when you look at this graph, what do you think it is? It's more plastic than elastic. When you look at the area under the curve. But when you look at the elastic strain values, they are 50-50. Right? So which one is right? Both are right, right? It all depends upon how you look at it. As long as you do the same analysis for all your sample, you are good to go. Easy method is this, difficult method is this. On the other hand, if you have software which does everything for you very highly accurately, this may give you more information than this one. So at the end of the day, you are the judge, right? Right? You make the decision. So you decide what is right for you. And you are always right. Right? We are always right, right? Yes or not? Yeah, we have to be right. When you take the exam, whatever answer you put, that's the right answer. Whatever professor thinks, it's his problem or her problem. We don't care about it. Whatever we write, that's the right answer. That's what we know, that's what we say. Right? It's up to the professor whether he or she want to give the marks or not. That's a different story. I mean, that's always I look for in my exam. That's what I'm telling you. I always tell people, give me assumption you make, tell me why you got the answer you got, and I will accept your reasoning. We all make mistakes, it's okay, but just tell me. So I will always accept when people say, this is how I assume, this is what I got. If the process is correct, I will give 100%. It's not my answer is the right answer. It's everybody's answer is right answer. It all depends upon how you look at it. Makes sense? I mean, even if you look at this case, if one person look at this way, different answer. One person looks this way, different answer. For the same problem. So anything is possible. It all depends upon how you look at things. As long as you explain your reasoning, you are good to go. Sometimes we do not explain the reasoning. That's why we get low marks. We get dodged for no reason. So if you give some reasoning, I'm just telling you in my personal opinion, okay? Don't take it for granted, because I don't want to make professors here bad professors. But everybody is good professor, but all different thinking process. And plus we cannot change people's mindset. Everybody has their own mindset, and that's how they are going to live with that. That's how we are going to live with that. So for whatever reason. So be strong in your conviction. Whatever conviction happened, be strong with that and tell the people, this is what I feel it is. Life is good. You don't have to. You don't want to make people change their attitude and then expect them to change the way you want. Let them be themselves. Let us be ourselves. There's no problem there, right? So be strong in your convictions. Tell their thing. This is what I'm thinking it is. So be it. Okay, I think we are running short of time. I think we are still recording things. So this is how you calculate the percent elasticity. Okay, we are going to do one more calculations. Okay, this is your classical example. This is loading curve. This is unloading curve. So let's calculate one by one. Stress data, strain data. Previously we had force, deformation and all. It's very straightforward. Everything is calculated for you, stress and strain. First thing is stiffness in Pascal. Can somebody shout at me, what is your stiffness value? Here, what is your stiffness value from this data? Huh? Hello? 0.7? Where is that come from? 225. This one is 225. Yes? Okay, this is 225. Okay, where is 0.7? This is 0.7. Stiffness in Pascal. Okay, let's go back. What is the stiffness? Well, how do you calculate the stiffness? Stiffness is initial slope during loading curve. Let's get this straightened out. So you calculated stiffness as 225 divided by 0.8. 175? You changed it. 175 divided by 0.7, which gives you 250 Pascal. Anybody in the center column, center column, row column? Anybody has any different answer? Can it be different answer? Yes, no? No? Why not? 150 divided by 0.6? 150 divided by 0.6, which is same as 250. Because it's a straight line, linear straight line, so any value you take, you get the same slope, so same stiffness. This is primarily to confuse people. But if you are doing your own way, everybody should get the same answer. If you are doing it in this same curve. Okay. Tangent modulus in Pascal at a strain of 0.4. So this is 0.4 and this is tangent modulus, which is tangent modulus is this. So slope at this point, same 250. Right? Answer A, answer B, same answer. When it comes to exam, you get confused, right? How can Muthu give me the same answer for part A and part B? This cannot be true. Muthu is tricking me. Different answers should be different, right? No, that's why I keep telling you. Go with your conviction. You tell me. If it is 250, it's 250. That's what it is. There is no brain here. There is no brainer. Degree of elasticity and degree of plasticity. Okay. So again, simplest method is this is elastic and this is plastic. So this is plastic and this is elastic. We recovered this energy. This is last energy. So degree of elasticity is 0.6 over 0.8. Degree of plasticity is 0.2 over 0.8, which is 75%. This is 25%. More elastic, less plastic. All is with me? Okay, let's keep going. Tensile testing. So far we looked at the compression, tension, same thing. I thought they are discussing more seriously, so they are going to ask me to close it, but that's okay, we have time. So tensile testing is similar to compression. Instead of compressing it, you are tensioning it. The same equations apply. There is nothing difference here. Only difference is because of the tensile, it's a tensile strength or tensile stress. Strain, tensile modulus. Here what happens when you are tension, the height increases. So h plus delta h is it's a final elongation, and then area is decreasing, right? As much as it elongate, this side should shrink because volume, right? So same volume, except that if there are some pore spaces, then we need to account for, and then Poisson ratio play a role. Poisson ratio will be the same thing for the same material, whether it is compression or tension, right? Because we are assuming it's a cohomogeneous material, pore spaces will be the same whether you are doing compression or tension. Why people don't do the tensile test at all? Always it's compression test only, right? Why not tensile test? Anybody thought about that? Why not?
The degree of elasticity for food materials will be less.
Degree of elasticity?
For the food materials will be generally less, so they are going to
Okay. According to her, your name again? Niveta, okay. According to Niveta, she thinks degree of elasticity is more for compression and degree of elasticity is less for the tensile, right? Yes? It's okay, I mean, it's what it, I mean, be yourself and whatever your mind is saying, just tell me. So, I don't think that matters that much in my opinion. Whether its degree of elasticity is higher or less doesn't matter. What's that? After tensile test, food material will break. For that matter, even compression also food material breaks. Yeah, it's compressed, right? But it's break. Right? Yeah, okay. Madam, your name? Anjali. Anjali says it's easy to do compression test than the tensile test. 100% correct. Because it's easy to compress. You can put something on top of it. But it is difficult to hold the sample and do the tensile test. The important thing about tensile test is if at all it breaks, only if it breaks in the middle, it's a correct test. So what I'm saying is, if this is your sample, okay, if this is your sample, you are doing tensile here, you have to hold in both places first of all, right? You need to have a clip to hold them, and then you need to pull apart, right? Chances of the clips coming out during the tensile test is very, very high. This may not hold it here. Even if the clips hold that material, chances of breaking at the middle, very, very slim. If at all it may break here like that. It very difficult to break at the middle. Only if the sample breaks at the middle, then the test is correct. And the values you get it's correct. If not, that test is worthless. And if you have multiple samples to do this test, it's a lot of time consuming. That's why Anjali said, compression is easy to do it, let's do easy test, get the data, life is good. Let's not go to a lot of complicated things. Why we want to do complicated things when we are going to get the same result, right? Your numbers may be different, who cares? I'm comparing only different samples here. I'm not comparing different test method. And nobody is going to give me an award for comparing different test method, right? Because my objective is to compare the samples so that I can prove that my treatment sample is better than my control samples. That's the bottom line, right? Or better than a control sample, or at least close to control sample. I don't want to prove that my sample is bad compared to control. Nobody is going to care about it. Okay? Good point. Thank you, Anjali. Thank you for the discussions, very important discussions. But the bottom line is, test is more important, less time. I mean, we all want to go an easy route, right? Same equation you use for tensile elasto. Same way you calculate strain, same way you calculate the modulus. Same thing. We are nearing ending the presentation. We talked about before this morning, brittle and ductile. So brittle samples will break immediately when you elongate them. The ductile sample will keep elongating, and then they will break. Right? That's the difference between brittle or ductile. Whatever happens, if you do this test, make sure that you break it in the middle. Otherwise, this test is no good. If it breaks here, it's no good. So that's why people don't do this test. We do easy test. Last but not least, as specimen deforms, stress calculated changes. So as it deforms, the calculated stress changes because the area is same here, but the areas keep changing. So when you calculate the stress over strain for different, both the ductile and the brittle samples, what happens is the engineering stress is different than true stress. The ductile samples, engineering stress, same area. So you have the plastic region and you will have an ultimate strength. The stress will keep increasing up beyond the ultimate strength for the ductile material. For brittle material, the stress will be decreasing after ultimate strength attains, and that's a difference. So this is a classic example for the brittle material and ductile material. Stress over strain. Thank you all. Nice talking to you, and thanks for listening.